Okay, calorimetry. It's the science of measuring heat flow. Our topic today really will be just measuring heat. But a calorimeter looks like this. You do not need to copy the diagram down. And I will hold off on really walking you through what a calorimeter does until next time. But our topic today is within the broader topic of calorimetry. First, let's look at temperature. Temperature is a measure of the average kinetic energy of the particles of a substance. Kinetic energy is the energy of motion. Anything that is moving has kinetic energy. Kinetics means motion. The equation that we could use to calculate kinetic energy is 1/2 times the mass times the velocity squared. Now, we do not need that equation for anything we'll be doing, but we do want to look at the relationship between velocity and kinetic energy. When the velocity is 0, meaning that there's no motion at all, well, then the kinetic energy would be 0. This temperature is called absolute 0, which on the Celsius temperature scale occurs at a negative 273 degrees Celsius. But it is the basis for the Kelvin temperature scale. It's based on that 0 point. So let's look at the relationship between the Celsius temperature scale and the Kelvin temperature scale. Okay, so this is the Celsius temperature scale. The 0 point of the Celsius temperature scale is the freezing point of water. So when water freezes, we call that 0 degrees Celsius. When we heat water up till it begins to boil, we call that 100 degrees Celsius. That defines the Celsius temperature scale. Now, the size of the degree, if we just keep counting down, so this is 0, and if we keep counting down at negative 273, that is the absolute 0. That is as cold as anything can get. And again, that's what defines the Kelvin temperature scale. So if we count up, and a Kelvin is exactly the same size as a degree Celsius, if we count up to 273 kelvins, we would be at the freezing point of water. Count up another 100 kelvins, 373 kelvins, we would be at the boiling point of water. So the two temperature scales are directly related in as far as the size of the units, but the 0 points have different definitions. 0 degrees Celsius is the freezing point of water. 0 kelvins is absolute 0. To convert from one unit to the other, kelvins is equal to degrees Celsius plus 273, and degrees Celsius is kelvins minus 273. Note that change in degrees Celsius is exactly equal to change in kelvins. The units have the same size, meaning if something increased its temperature by 10 degrees Celsius, it would be exactly the same as increasing the temperature 10 kelvins. The size of the units are exactly the same. The only difference is the 0 point. Heat. Kinetic energy transfer at the molecular level. Heat only moves in one direction, from high temperature to low temperature. So let's take a look at this. Imagine that this is a piece of metal, and we're heating one end of it. Well, what will happen is that the atoms of the metal will begin to vibrate, and they'll knock into other atoms, which will knock into other atoms, and on and on and on. Imagine if this was just a bunch of ping pong balls and you hit one end, well, the kinetic energy, the balls would just hit other balls, and it would transfer over. That's what happens when we heat something up. We heat up one end and that heat transfers over. But on the molecular level, it's just as simple as I said with the ping pong balls, just imagine them knocking into each other. That kinetic energy transfers through. So always high temperature to low temperature. Specific heat is given the symbol lowercase c. The heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. has the units of joules per gram degree Celsius. Both grams and degrees Celsius are in the denominator. Or we could say joules per gram kelvins. I don't know if I mentioned before, but we say degrees Celsius, but we don't say degree kelvins. We just say kelvins. Here are some examples, specific heats. You don't need to copy this down. Let's use iron as an example here. So the specific heat of iron is 0.45. So what does that mean? Well, it means that if we had a 1 gram sample of iron, in order to raise its temperature, whatever temperature it's at, 1 degree Celsius, to increase its temperature 1 degree Celsius, we would have to supply 0.45 joules of energy. So 0.45 joules would be needed to raise 1 gram of iron 1 degree Celsius. Let's look at water. Now, water's specific heat is 4.18 joules per gram degrees Celsius. Now, that's going to be a very important number. We'll be using it a lot when we get to calorimetry. Now, that is, in fact, also the definition of a calorie. 1 calorie is 4.184 joules per gram degrees Celsius. A calorie is the amount of energy necessary to raise 1 gram of water 1 degree Celsius. We could also say 4.184 joules per gram kelvins. Now, you're going to see in your IB textbook, not written like this, but written like this, where we use a -1 for any unit that's in the denominator. So it means exactly the same thing. So I don't want you to freak out if you should see that. That's the way we do it in the IB world. But we'll be using this, joules per gram degrees Celsius. Okay, now this you might find interesting. This is just FYI. 1,000 calories, these calories defined as we just did, is what we mean by a kilocalorie or a big calorie, 1 big cal. That's what how they call it, a big cal. Is, in fact, a nutritional calorie. Nutritional calories are the calories you're familiar with, found on food packaging. So this, it says it's the calories is 180. Well, it's not 180 of these calories. This definition, it would be 180,000 calories, because these are nutritional calories. 1 nutritional calorie is equal to 1,000 calories as we defined up here. This is called the heat transfer equation, and we'll be using this to do some calculations here in just a second. So let me define each one of these terms. Q is what we use to mean heat. So it'll have units of joules. C is specific heat that we just talked about. M, of course, is mass. And delta T is the change in temperature. Remember, it's always final minus initial. Talked about that last time. So final temperature minus initial temperature is our delta T. Okay, so let's see how we can use this equation to calculate any variable here that we don't know, given that we know the others. Let me say that again. We can use this equation to calculate any unknown variable if we were given the others. Right, so let's do a practice. How much heat will be needed to raise 10 grams of aluminum from 22 degrees Celsius to 36 degrees Celsius? Well, we're going to need to know the specific heat of aluminum to do that, and it is 0.987 joules per gram degrees Celsius. Okay, now to solve these problems, what you will want to do is to first take the word problem and summarize it using the variables from the heat transfer equation. So the question is asking how much heat? Well, Q is heat, so that's what we don't know, but we know everything else. We know the specific heat, 0.987. We know the mass, 10 grams. And we know the change in temperature. It went from 22.0 degrees to 36 degrees. So remember, it's always final minus initial. So final minus initial, and that gives us 14 degrees Celsius. So now we know everything. We know C, M, delta T, and we can plug those in to calculate Q. So let's do that. So the specific heat, C, the mass, 10 grams, and the change in temperature, 14 degrees Celsius. Okay, notice that grams cancels out, degrees Celsius cancels out, leaving us nothing but joules, which is what we want, because remember Q represents heat, and the unit for heat would be joules. So 138 joules. We're limited to 3 sig figs. Let's try another one. Determine the specific heat of an unknown metal if it requires 52.5 joules of heat, 52.5 joules to heat a 10-gram sample from 10 degrees Celsius to 25 degrees Celsius. Okay, so let's again take our word problem and summarize it using the variables from the heat transfer equation. So Q is 52.5 joules. The specific heat is what we're trying to determine the specific heat. So that's what we don't know. But we do know the mass, 10 grams, and we do know the change in temperature. Went from 10 degrees to 25 degrees, so 25 is our final, 10 is our initial. So final minus initial gives us 15 degrees Celsius. Okay, now we're going to need to solve for specific heat. So our main equation, of course, is Q is equal to Cm delta T. We know everything except for C. So let's first solve for C algebraically. So if we divide both sides by m delta T, we would get that C, specific heat, is equal to Q divided by m delta T. So all I did was divided both sides by m delta T, and that would be what C, specific heat, is equal to. So now I can just plug in all of the values that we know. So Q is 52.5 joules, M is 10 grams, and the change in temperature is 15 degrees Celsius. Now, unlike the problem that we just did, notice that nothing cancels out. Joules, grams, degrees Celsius, well, that's good because that is the unit of specific heat. Remember, joules per gram degrees Celsius. So this gives us 0.350 joules per gram degrees Celsius. So this might give you a better sense on why we have those units. Joules per gram degrees Celsius, heat divided by mass divided by temperature gives us those units. All right, so these are the two problems that you want to use as a reference to do your homework. But for now, that is the end of notes.